Two blocks with mass m1 and m2 are connected by a light spring with spring constant K and sit on a rough level floor, as shown in the figure below. The spring is at its original length L. A pulling force F is applied to block 2 and pulls the whole system to the right with a constant velocity. Assume the kinetic friction coefficient between the blocks and the floor is mu K. What is the length of the spring and the pulling force? So let's start by drawing some free body diagrams for both. So for block 1, let's draw this. So here is block 1. You have the normal force acting up. And since they have different masses, I'm going to call it normal 1. You have the force of gravity, which is m1 times g. Again, they have different masses. You have the force of kinetic friction, dragging it back. And you have the spring force. Oh yeah, and they also have different kinetic frictions. I'm just going to leave this as just Fk. Since they have different masses, they have different kinetic frictions. So this is for block 1. Now we can do the same thing for block 2. It's probably better if I drew it up here, actually. So I'm going to redraw this up here. So this is block 1. Just redrawing it up there because there's more space. And then for block 2, again, we have the normal force and the force of gravity acting on it. But these have different magnitudes because their masses are different. Here we have the pulling force. And then there are actually two forces pulling it back. You have the spring force from Newton's third law. It's pulling block 1 forward, so it must be pulling block 2 back. And adding on to that, we also have the force of kinetic friction. And this force of kinetic friction is different from that of block 1 because they have different masses. So this is block 2. So now that we have that, we can set up some equations. First, let's say, you can say that the spring force minus the kinetic friction force must equal the mass times acceleration, which equals 0, since the whole system is in dynamic equilibrium, since it's moving at a constant velocity. So because of that, we can say that the spring force is simply equal to the force of kinetic friction in block 1. It's important to distinguish between the two blocks. So that's for block 1. From block 2, we get that the force minus the pulling force minus the spring force minus the force of kinetic friction on the second block is equal to 0. Again, this is equal to ma, which is 0 since the whole thing is in dynamic equilibrium. Now, solving for the force, we get that the force is equal to the spring force plus the force of friction from the second block. So there's that. Now, from this, we can substitute the force of the spring with the force of kinetic friction. So we can say that the pulling force is equal to the force of kinetic friction from the first block plus the force of kinetic friction from the second block. And that is why we even use this equation in the first place. So there's that. And now, if you remember, the force of friction is the coefficient of kinetic friction times the normal force. In this case, for block 1, it is the coefficient of kinetic friction times the mass, times its mass, times its gravity. And this is the same thing for block number 2, which has its own normal force and its own mass. So now, if you look at these two, you can substitute these in, which is equal to UK times G times M1 plus M2. And again, since these two both have mu K and G in common, I just factor them out so that I don't have to write as much. So that's one part of the problem done. The pulling force is equal to the coefficient of kinetic friction times the acceleration due to gravity times the sum of both of their masses. So that's the pulling force. Now we need to figure out the length of the spring as it's being pulled. So there is a thing called Hooke's law. It's H-O-K, Hooke's law, that says that the force of a spring is equal to the negative of the spring constant times the displacement. And this negative is just there if you don't know the direction. It's simply saying, the negative sign is simply saying that this force acts in the opposite direction of the displacement. So it's going to oppose the displacement. But we already know the directions. We already have that figured out. So we don't really need this. But if we do look at this, we can just use the free body diagrams to figure that out. So from that, we can say that in our case, spring force is equal to the spring constant times the change in length of the spring, which is simply the spring constant times the new length minus the original length. And if you remember from earlier, we figured out that the spring force is also given by the force of kinetic friction of the first block. So now we can substitute that the spring force is equal to the coefficient of kinetic friction times the mass of the first block times G. And now, if you remember this part here, you can substitute that in for the spring force. So we can say that the spring constant times the change in length is equal to the coefficient of kinetic friction times the mass times the gravity. There's that. Now all we need to do is solve for the new length. And that is equal to coefficient of kinetic friction times the mass times gravity divided by the spring constant plus the original length. So that's the third part, or sorry, the second part. So the new length of the spring is equal to the coefficient of kinetic friction times the mass of the first block, not the second block, times the gravitational acceleration divided by the spring constant plus the original length of the spring. And that is how you would solve this problem here.